In just 10 hours of testing, a single telescope on a mountaintop in Chile found more than 2,000 asteroids we never knew existed, and that was before it even officially started its job. If you've been waiting for the next era of astronomy to begin, it already has. And what you're about to see will completely change how you think about our place in the universe. For decades, astronomers dreamed of a telescope that wouldn't just peer at the universe, it would watch it. Not like a scientist hunching over an eyepiece, choosing one star, one galaxy, one sliver of sky, and waiting. But like a surveillance camera bolted to the cosmos itself, scanning, logging, repeating, never blinking. A machine that treats the entire southern sky not as a destination to visit occasionally, but as a canvas to rephotograph every few nights for 10 straight years. That dream now has a name, a mountain, a mirror, and the most extraordinary camera ever assembled by human hands. This is the Vera C. Rubin Observatory, and its first images have just arrived. The facility sits atop Cerro Pachon, a peak in the Chilean Atacama Desert at roughly 2,682 meters above sea level, where the air is so dry and the night so clear that astronomers have long considered it sacred ground for observing. It doesn't stand alone up there. The European Extremely Large Telescope, the Gemini South Observatory, the Giant Magellan Telescope, and the Southern Astrophysical Research Telescope are all neighbors on these ridgelines, but the Rubin Observatory is fundamentally different from every one of them in both philosophy and design. It is not funded by a traditional space agency like NASA or ESA. Instead, it was built through a partnership between the US National Science Foundation and the Department of Energy, managed by the Association of Universities for Research in Astronomy, and supported by international partners across more than 3 decades of planning, engineering, and construction that formally began in 2015. At the heart of the facility is a telescope formerly called the Simony Survey Telescope, which became the 7th largest telescope in the world when it was completed. Its primary mirror stretches 8.4 meters across, wider than the mirror aboard the Hubble Space Telescope. But here's what makes it genuinely unusual. Where most telescopes rely on 2 mirrors to gather and focus light, the Simony Survey Telescope uses 3. Do a primary mirror at 8.4 meters, a secondary at 3.5 meters, and a tertiary at 5 meters. This 3-mirror anastigmatic optical design is the key to one of Rubin's most jaw-dropping capabilities. An extraordinarily wide, flat field of view spanning approximately 9.6 degrees of sky. To put that in human terms, you can see about half a degree of sky with your naked eye when looking at the full moon. Rubin sees roughly 45 full moons at once in a single snapshot. That is not a metaphor. That is the actual field of view, and it is the foundation for everything this observatory is about to do. Attached to the rear of this 3-mirror optical system is the instrument that has already set records before the telescope has even entered full operations. The Legacy Survey of Space and Time camera, known as the LSST camera. At approximately 3 meters long and 1.6 meters wide, and weighing about 2,800 to 3,000 kilograms depending on the source, it is the largest digital camera ever constructed for astronomy. Not the largest among ground-based telescopes, not the largest since some earlier era, the largest ever, full stop. Its focal plane is assembled from 189 individual charge-coupled device sensors stitched together into a single seamless imaging surface. The resolution achieved by this arrangement is 3.2 billion pixels, 3,200 megapixels per exposure. To display a single full resolution Rubin image, you would need approximately 385 4K ultra-high definition television screens arranged side by side. The sensor array operates at cryogenic temperatures, requiring a specially designed cooling system just to keep it stable enough to function without generating thermal noise that would corrupt the data. The camera cycles through 6 filters, spanning from ultraviolet through optical wavelengths and into the near-infrared, and can take a full wide field image in 30 seconds, slew the telescope slightly, and take another. Repeat that all night, every clear night, and you begin to understand the scale of what Rubin is designed to produce. Approximately 20 terabytes of raw data every single night. For comparison, the Hubble Space Telescope generates about 8 terabytes of data in an entire year. The James Webb Space Telescope, far more advanced than Hubble, collects around 200 terabytes annually. Rubin, in one night of operation, will outpace Hubble's yearly output by more than a factor of 2. Over its planned 10-year mission, it is projected to generate somewhere in the range of 500 petabytes, 500,000 terabytes, of data containing measurements of billions of objects. Because of the sheer volume, a dedicated 100 gigabit internet connection was constructed specifically to transfer data from Chile to a processing center in the United States, tapping into existing infrastructure at Miami, Florida. And all of that raw data flows into a processing pipeline powered by artificial intelligence. Without machine learning, this dataset would be essentially unmanageable. The AI systems are built to compare each new night's images against a template, a reference mosaic of what each part of the sky looked like in previous observations, and flag anything that has changed, moved, brightened, dimmed, appeared from nowhere. This technique, called difference imaging, is the mechanism by which Rubin will detect an estimated 10 million changing objects every single night of its operations. Supernovae flaring and fading over days, asteroids drifting between frames, variable stars pulsing in their ancient rhythms, black holes waking up and flaring in distant galactic cores. None of it will escape notice. The alerts generated by this pipeline are shared in real time with observatories around the world, allowing follow-up observations to begin within minutes of detection. The first images, officially released in June 2025 and taken during April and May of that year, have already demonstrated something extraordinary. This machine is functioning beyond expectations even in its earliest test phase. Before discussing what those images show, it's worth pausing to appreciate what it takes to make them. Unlike a space telescope, the Rubin Observatory operates inside Earth's atmosphere, which shimmers, distorts, and blurs light in ways that can ruin an astronomical image, managing this atmospheric interference over thousands of individual exposures, while also dealing with light from passing satellites, cosmic ray strikes that leave streaks across the sensors, and the constant gravitational flexing of a massive optical system as it tracks objects across the sky requires engineering precision of an almost absurd degree. The images you are about to see are not just pretty, they are scientific instruments disguised as photographs. The headline image from Rubin's first light is a mosaic the team has nicknamed the Cosmic Treasure Chest. It is a composite assembled from 1,185 individual exposures taken over 7 nights, covering 25 square degrees of sky in the southern portion of the Virgo cluster, the nearest large galaxy cluster to our own Milky Way, located approximately 55 million light years away. The image combines data taken through 4 filters, ultraviolet, green, red, and near-infrared, to produce a color composite that contains far more information than any single wavelength could convey. And when you look at it, really look, you begin to understand that you are staring at a cross-section of the universe itself, layered in depth from our own cosmic neighborhood out to the edge of what we can see. The bright, spiked stars scattered across the image are foreground objects in our own Milky Way, their light so intense that it diffracts around the telescope's support structure into those characteristic rays. They are millions of times closer to us than anything else in the frame. Behind them begins the real content, a staggering tapestry of approximately 10 million galaxies, not 10 million stars, not 10 million objects of some uncertain type, 10 million entire galaxies, each one a collection of billions of stars, each one a universe unto itself, captured in a single mosaic image covering just 0.05% of what the Rubin Observatory will eventually survey. Zoom into the upper left region of this mosaic, and the first major feature that resolves itself is Messier 49, a colossal elliptical galaxy glowing with a soft, warm yellow light. The elliptical galaxies are, in a sense, the retirement communities of the cosmic world. They are filled with old, cool stars in colors ranging from yellow to red, stars that formed billions of years ago when these galaxies were young and productive. Messier 49 stopped forming new stars a long time ago. Its quiet glow tells you everything about its age and history. Just to the left of M49 sits NGC 4535, and the contrast is immediate and striking. Where M49 smolders in soft amber light, NGC 4535 blazes with blue and white, a face-on spiral galaxy actively forming new stars right now, today, at this moment in cosmic time. Its spiral arms are packed with clouds of gas and dust in which hot young stars are being born. Blue and white in a galaxy image are the colors of youth, of energy, of stellar nurseries at their most active. The two galaxies sit in the same field, not because they are physically close, they are separated by significant distances, but because Rubin's field of view is so vast that galaxies, which would normally require completely separate telescope pointings, are now neighbors in a single frame. Move further across the mosaic and you encounter what may be its most scientifically spectacular feature, a triple galaxy merger caught in the act of collision. Three galaxies, each once a coherent spiral or elliptical structure with its own identity, are now pulling at each other gravitationally. Their stars and gas stretched into long tidal tails, bridges, and arcs of luminous material. The shapes are distorted, twisted, folded, and yet within the chaos you can still make out hints of the original spiral arms before the violence began. Galaxy mergers are not rare in cosmic history. The Milky Way itself has consumed smaller galaxies throughout its lifetime and is currently on a multi-billion-year collision course with the Andromeda Galaxy. But catching one in the act with this level of detail from the ground is remarkable. When galaxies merge, star formation surges as compressed gas clouds collapse. Supermassive black holes at galactic centers approach each other and eventually merge. The entire event reshapes the identities of the galaxies involved, often producing massive elliptical galaxies from the remnants of two or more spirals. In one area of this single mosaic, you can watch this billion-year drama frozen at a single moment in time. Just below the merger, the two face-on spiral galaxies appear side by side as though they are a pair in close orbit, but this is a trick of perspective. One of them is approximately 20 million light-years farther away than the other. They have no gravitational relationship whatsoever. They simply happen to appear close together from Earth's vantage point, a reminder that a two-dimensional image of the three-dimensional universe can deceive you if you don't account for depth. And scattered throughout the background, in the faintest reddish smudges at the very limit of detection, are galaxies far beyond the Virgo cluster, some more than 1 billion light-years distant. Their light left them when multicellular life on Earth was still a relatively new experiment. Now zoom into the region the team has labeled cosmic drama on the opposite side of the mosaic. Here, foreground Milky Way stars blaze in the immediate foreground, while dozens of nearby galaxies crowd the middle distance. And behind all of them, like embers scattered across dark water, a vast population of reddish, faint, distant galaxies forms a continuous backdrop stretching to the edge of the observable universe. Many of these galaxies have never been catalogued before. Many have never been detected by any telescope. They are not in any database. They have no names, no coordinates, no entries in any astronomical literature. They are simply there, suddenly visible, waiting for astronomers to begin the work of understanding them. And yet, galaxies are only part of the story. hidden in the same image, leaving colorful streaks across individual exposures before being algorithmically removed from the final stack, are asteroids, dozens of them in every frame, cutting diagonal trails across the field as they drift through the solar system during Rubin's long exposures. In just 10 hours of early test observations, the observatory detected 2,104 asteroids that had never previously been catalogued. That number includes 7 near-Earth objects, asteroids with orbits that bring them into the general vicinity of Earth. None pose an immediate threat, but their detection illustrates something critical about Rubin's potential. We currently have complete orbital information on roughly 40% of the near-Earth objects large enough to cause serious regional damage if they were to strike. The rest are out there, unknown, untracked, uncharted. In 2013, a 20-meter asteroid approaching from the direction of the Sun exploded over Chelyabinsk, Russia, releasing energy equivalent to roughly 500 kilotons of TNT, more than 30 times the Hiroshima bomb, shattering windows and injuring over 1,600 people. It had not been detected, no warning was issued, it was simply not in anyone's catalog. Rubin is designed to change this equation systematically over the next decade. It is expected to discover millions of new solar system objects, asteroids, comets, outer system bodies in unusual orbits, perhaps including the long hypothesized Planet 9 that some researchers believe lurks in the distant reaches of the solar system beyond Neptune. More critically, Rubin's consistent cadence, imaging the same patches of sky every few nights, tracking the movement of objects between exposures, provides the kind of long-term orbital data that makes early warning possible. An asteroid discovered with 10 years of advance notice is a solvable problem. An asteroid discovered 2 days before impact is not. The second major image released from Rubin's early operations takes us into our own galaxy, not to survey billions of distant objects, but to look at 2 luminous clouds of gas and dust relatively nearby on cosmic scales. This is the combined mosaic of the Lagoon Nebula and the Trifid Nebula, assembled from 678 individual exposures taken over approximately 7 hours. The Lagoon Nebula, also designated Messier 8, sits roughly 4,000 to 5,200 light-years away in the constellation Sagittarius. It is one of only a handful of star-forming nebulae visible to the naked eye from Earth's surface, though only faintly, and only from certain latitudes. Through binoculars or a small telescope, it appears as a smudged gray cloud. But Rubin records it in ultraviolet, optical, and near-infrared light simultaneously, then assigns those wavelengths to colors the human eye can interpret. Blue for the hot ultraviolet emission of young massive stars, red for the cooler infrared glow of dust and gas, and the result is a living, glowing structure of extraordinary beauty and scientific richness. The comparison to Hubble's view of the same object is instructive. Hubble's famous 2018 image of the Lagoon Nebula is extraordinary in its detail, sharp, rich, layered with information about individual stars and gas structures. But Hubble's image covers approximately 4 light-years across, a tiny window into a nebula that is actually 55 light-years wide and 20 light-years tall. Rubin shows the entire Lagoon Nebula and much more. The Trifid Nebula at the top of the frame, a young open star cluster designated Messier 21 above that, another open cluster called Bochum 14 below, and toward the bottom, a tightly packed globular cluster, NGC 6544, containing tens of thousands of ancient stars compressed into a dense sphere. Hubble sees 1% of the moon's apparent surface area in a single image. Rubin sees 40 times the moon's surface area. That means in any given exposure, Rubin can photograph approximately 4,000 times as much sky as Hubble, with a camera 190 times more sensitive in terms of pixel count. These are not incremental improvements. This is a different category of instrument. Underneath everything the Vera Rubin Observatory does lies a mission that feels almost poetic given the name it carries. Vera Cooper Rubin was an American astronomer who, working in the 1970s with what now seems like modest equipment, measured something that should have been impossible according to the physics of her time. She tracked the rotational velocities of stars at different distances from the centers of galaxies and found that the stars on the outer edges were orbiting just as fast as the stars near the center, sometimes faster. According to Newtonian gravity and the observed mass of the visible stars, they should have been moving much more slowly. The only way to explain what she observed was to conclude that there was additional invisible mass distributed throughout and around these galaxies, providing extra gravitational pull. She called it what it was: missing mass. Science eventually called it dark matter. Rubin's observations, repeated across multiple galaxies with rigorous methodology, established what is now considered one of the foundational discoveries of modern cosmology. She never received a Nobel Prize for this work, a fact that many scientists consider one of the most significant oversights in the history of that award. She passed away in 2016. The observatory was named in her honor in 2019. The connection between her name and this telescope's mission is not merely honorific. One of the 4 primary scientific goals of the LSST survey is to investigate dark matter and dark energy, the invisible substance Rubin helped discover, and the mysterious force that is causing the universe to expand at an accelerating rate. The method the Rubin Observatory will use is called gravitational lensing. When light from a distant galaxy travels through the universe toward Earth, any massive object it passes near, a galaxy cluster, or a large concentration of dark matter, will bend its path slightly, distorting the apparent shape of the distant galaxy. This effect, predicted by Einstein's general relativity, leaves subtle signatures in the shapes of billions of background galaxies. Rubin's camera is precise enough to measure these tiny distortions across the entire southern sky, galaxy by galaxy, frame by frame, year by year. By mapping where and how strongly space-time is being curved, astronomers can reconstruct a 3-dimensional map of the dark matter distribution throughout the observable universe, not just in a single cluster or along a single line of sight, but across the entire cosmos. That map, built over 10 years from billions of lensing measurements, will be the most detailed portrait of dark matter's structure in the universe ever assembled. Vera Rubin measured the invisible with a spectrograph and a notebook. The observatory that bears her name will chart it with a 3.2 billion pixel camera and 500 petabytes of data. What is happening here, and it is worth saying plainly, without hyperbole, is a genuine revolution in how astronomy is practiced. For centuries, the discipline depended on decisions: which object to point at, which night to observe, which field to prioritize. Even the most productive sky surveys of the previous generation, like the Sloan Digital Sky Survey, which took 20 years to map 35% of the sky, operated on a fundamentally limited cadence. The Rubin Observatory will do what SDSS accomplished in 20 years every 3 days, and then it will start over, and it will keep going for 10 years. The cumulative effect of that repetition, not just seeing the universe but watching it change, will produce the first true time-lapse of the cosmos. Stars will pulse and flare, supernovae will ignite and fade, asteroids will drift through their measured orbits, galaxy pairs will edge incrementally closer over the decades of the survey. All of it will be logged, time-stamped, and archived, and in a decision that may prove to be one of the most consequential in the history of open science, all of this data will be public. The images, the object catalogs, the time series light curves, the real-time alerts, all accessible to anyone with an internet connection. Professional astronomers at major institutions will mine it. Graduate students at smaller universities will find their thesis topics within it. Citizen scientists will contribute to genuine discovery. AI systems trained on its outputs may identify patterns that no human would have thought to look for. The next generation of astronomers is growing up right now, and some of them will make their most important discoveries not at a telescope eyepiece, but at a laptop, combing through a dataset that didn't exist until this year. The survey hasn't even formally begun. These early images, the cosmic treasure chest, the Lagoon Trifid mosaic, the swarm of newly discovered asteroids, are proof of concept demonstrations, capability tests run while the final systems were still being calibrated. The real survey, with its relentless 10-year cadence, it is just starting. And yet in those first 10 hours, 2,104 new asteroids. In those first 7 nights, 10 million galaxies in a single frame. These numbers are not exaggerations or projections. They are what already happened. The universe has always been in motion. Supernovae have always exploded. Asteroids have always drifted through their silent orbits. Galaxies have always been colliding, merging, evolving. We simply lacked the tools to watch. Now, on a mountain in the Chilean desert, a 3.2 billion pixel camera is awake and watching, and it will not look away for a decade. What it finds will rewrite our understanding of dark matter, of planetary defense, of how galaxies live and die, of what the solar system contains that we have not yet catalogued. It might find the rogue planet some theorists predict is hiding in the outer darkness beyond Neptune. It might catch the next Chelyabinsk rock before it arrives. It might reveal structures in the distribution of dark matter that force a fundamental revision of our best cosmological models. Or it might show us something none of us have imagined yet, because that is what happens when you stop choosing what to look at and instead decide to look at everything. Tell us in the comments below. Which of these first images blew your mind the most? The 10 million galaxies of the cosmic treasure chest, the ethereal glow of the Lagoon and Trifid nebulae, or the quiet revelation of 2,000 asteroids we never knew were there? Subscribe so you don't miss a single update as the Rubin Observatory continues to open our eyes to the universe, because we are just getting started and this machine is just warming up.